We need to understand what is process analysis, and then process flow charting, types of processes, process performance matrix. So process analysis terms, process is any part of an organization that takes inputs and transform them into outputs. So actually, when it comes to operations, the processes are the primary things, and around the processes, organizational structures are also determined. And then cycle time is the average successive time between completions of successive units. So for an example, let's say take for example item 1. Say item 1 took 30 seconds, 2 took 35 seconds, 3 took 40 seconds, 4 took, let's say, 30 seconds again, and 5 took 35 seconds. So, we have now 5 observations. If you produce in the same same item took 30, 35, 40, 30, 35 seconds. So then the average, the first one took 30 seconds, second one took 35 seconds, third one took 40 seconds, fourth one took 30 seconds, fifth one 35 seconds. So we need to. So this is time between. This is time to produce first one. This is time to produce second one, third one, and so on. So this is then time between first and second is 30. The second and third is 35. Third and fourth is 40. Fourth and fifth is 30. And fifth item, okay. Up to the time from 5 to 6 is 35. So then the cycle time.
So excuse me, sir.
Yes.
Sir, here 30 seconds mean in the first step, it takes 30 seconds to produce the item. Is it so, sir? Okay, sir.
Second one, 35 seconds. Actually, it is time between the items. So the time taken, let's say first one came after 30 seconds, okay? Second one, and then second one came after first one, right? So then actually, let's say if you see things sequentially, the cumulative time, this is 30. Next one is 65. Next one is 105. Next is 135. Finally, 240. So then you see time to produce the first one is 30 seconds. And then from first one to second one is 35 seconds. See, from second one to third one is 40 seconds. So like that. And then cycle time is the average time. So we divide the 140 divided by 5. So this equals 65, 105, 135, then plus 35, 170, 170 divided by 5. So that's 30. So this is seconds. Then cycle time is, average time between the items. So you see, so here, let's say if you take if you want to calculate the cycle time from an ongoing production line, let's say you have to start somewhere, right? Then you have to start, when let's say a particular item is in process, you don't know when that one started, and then you want to observe the time for the next one. So you have to wait until that is finished, and then start calculating. Maybe you can use a stopwatch, and then start the moment the previous one is over. Use the one next one starts. So then start the watch, and then once it is finished, you stop the watch, and then again start the watch for the next one. So then that is the way to calculate the time for successive items. And then the cycle time is the average time between successive items. So this is how we calculate. Process analysis terms, we are discussing, is the average successive time between completions of successive units, right? And the utilization is the ratio of the time that resource is actually activated relative to the time that is available for use. So let's say a particular machine is available from, let's say it is available 24 hours, okay? And then we are using, or let's say we use 2 shifts, and then 8 hours, the other one 8 hours. So 16 hours. So then 16 divided by 24, that is about 66% is the ratio is 0.66 or 0.67 is the ratio, and that is the utilization. And then process flow charting. Process flow charting is the use of a diagram to present the major elements of a process. So the basic elements can include tasks or operations, flows of materials or customers, decision points, storage areas or queues. So this is an ideal methodology by which to begin analyzing the process. So, we use rectangle, to denote task or operations. This flow chart is similar. Example, giving an admission ticket to a customer, installing an engine in the car. These are tasks, okay, or operations. And decision points is a diamond. Example, how much change should be given to a customer, which range should be used. So these are decision points. Storage areas of queues, you denote by this type of triangle. Example, sheds, lines of people waiting for a service, etc. And then arrow is flows of materials or customers, or for that matter, movements. Example, customer we move into a seat, mechanic getting a tool, etc. These are flows of transportation. Example, flow chart of a school student going to school. And let's say he has to decide whether he goes to school or not. So then go to school today. And if he decide no, he will do other things. And then if he decides to school, then he has a process to go through, a task to go through, then drive to school, and then walk to class. Okay. And then types of processes, you have single stage processes. Single stage process means whole operation, total operation or total factory is one stage. And then multi-stage processes. So you have, these stages are sequentially arranged, 1, 2, 3. So you have the raw materials entering into the stage 1, and then you get the final output from the stage 3. So this is a sequential arrangement of multi-stage. We have 3 stages. The concept of buffer refers to a storage area between stages where output of a stage is placed prior to being used in a downstream stage. So you have, let's say, a two-stage processing with buffer. So you have, before the stage 2, you have a buffer. So this buffer means, can be inventory. So then after producing the stage 1, what is produced in the stage 1 is stored here in the storage. And then from the storage taken to produce in stage 2. And then buffer actually has a buffer's positive role is, let's say, the stage 1 and stage 2 capacities are different. Let's say if stage 1 is faster than stage 2, all produced all items processed in stage 1 cannot be used in stage 2. So there will be inventory. So then this particular inventory will act as the buffer between inventory, and then you can store them in this storage. So this inventory becomes a buffer, and then buffer actually helps function stage 1 and stage 2 independently. Otherwise, what will happen is if stage 1 is faster than stage 2, in order to avoid the inventory, stage 1 has to slow down the work. So slow down the work speed. Otherwise, there will be a lot of produced piled up, and not having place to put it down. So that is the important thing of a buffer. Buffer actually facilitate the stages to function independently. And then the other term, blocking. Blocking occurs when the activities in a stage must stop because there is no place to deposit the item just completed. If there is no room for an employee to place a unit of work down, the employee will hold on to it, not able to continue working on the next unit. So here, let's say you don't have a buffer. Imagine this situation. There are no buffers here. And then all the work worked out has to be taken by stage 2 worker. And then what is worked out has to be taken by the stage 3 worker. And then after stage 1 is worked down, he doesn't have a place. If stage 2 don't take it, okay? And then stage 1 person will have to hold on to it until this person takes it. So that situation is what we call blocking. So he will be holding on to it. So he is blocked from not blocked because he has work down on his hand. So not having a place to put down, so that he has to he is in the blocked situation. And then starving occurs when the activities in a stage must stop because there is no work. So if an employee is waiting at a workstation and no work is coming to the employee to process, the employee will remain idle until the next unit of work comes. So when an employee remains idle, not having work to do, so then the situation we call starving. And then bottleneck, the concept of bottleneck occurs when the limited capacity of a process causes work to pile up or become unevenly distributed in the flow of the process. Bottleneck happens when, let's say, if an employee works too slow in a multi-stage process, work will begin to pile up in front of that employee. In this is the case. In this case, the employee represents the. In this case, the employee represents the limited capacity causing the bottleneck. So why we have this concept bottleneck is why the term bottleneck is used. Let's say if Imagine shape of bottle. Okay, so roughly, right? So then, let's say imagine this is a pipe, okay? This is a pipe, right? And then water is coming that way. Then, since this here it is smaller, what will happen is, there will be a pressure created here, and there will be, you will see that water will blow from this place, and so it will blow like that. So why is it? Because of the pressure created over there, and so this is the situation of bottleneck. So let's say bottleneck can happen in traffic also. Let's say the road, when the road is traffic is coming, and then when you find a narrow pass, there will be a lot of traffic piled up in front of the narrow pass. So let's say, uh, so that's why we use the term bottleneck. So this is the narrow pass. Actually, it is the narrow pass which create the traffic congestion in front of the narrow pass. So the problem is the narrow pass. So similar, here is this narrow pass is similar to a slow working employee. For that matter, slow worker. That's why we use the term bottleneck in this. Other types of processes, you have make to order. So then make to orders are only activated in response to an actual order. So without an order, the production process is not working. So for example, in just-in-time methodology, what happens is, once you get an order, uh, order is supplied from the inventory. Okay, in just-in-time philosophy, we keep only minimum level of inventory. So we supply from the inventory, but at the same time, the production is activated to replace the inventory, so that you always have inventory uh, to uh, to to fill the order. But once the order is obtained, immediately production is activated, because what is in the stock will be sold. So that's how that is actually in just-in-time production philosophy. They use the make to order concept, and here both work in process and finished goods inventories are kept to a minimum. So by doing so, total cost of production is minimized. Total cost of production is minimized. And then make to stop. Here, process is activated to meet expected to forecast demand, and customer orders are served from target stocking level. So here, actually, it's different from make to order. So you see, the production is activated to meet the expected demand or expected forecast demand, and based on the expected forecast demand, product is produced and it's kept in the stock. Once the orders are received, it is supplied from the stock, or for that matter, inventory. So that's how make to stock work. Actually, make to order and make to stock, what is better? If the demand is definitely, the demand is sure. If the demand is sure, then make to stock is safer. And also, let's say, for example, a country like Sri Lanka. Sri Lanka situation is, nowadays this particular government is printing a lot of money, and then obviously money supply is greater in the market. So because of that, the produce will go up, the prices will go up, and then the better is produce and keep the keep the items in the stock, so that when the demand occurs, you can supply at greater prices. So if you produce, let's say today, and then if the rupee is going down, rupee depreciation happens and the prices will go up. So then let's say you will, in 1 month's time, you will sell at a higher price, but the production cost in terms of rupees is low. So if the economy, unstable economy, I think better to use the make to stock approach. For a stable economy where prices don't go up, and then you don't have surprises in the supply, and you see the make to order works well. So on the other hand, you have if the orders are actually let's say you can stock items in the inventory, but then if you don't get the demand, expected demand as it is, then you will have a big problem, because you have big inventory without being able to sell. So that risk is there when it comes to using make to stock. For an example, let's say a competitor produces um, let's say take for example now what can happen in the to the motor car industry. Motor car industry, there are two developments that are happening. One development is the people are, governments are pushing towards the electric cars, so that the pollution will be minimized. So that is one thing. The other thing is, uh, for example, electric cars are possibility, and also hydrogen cars. Japan, the Toyota Corporation has developed hydrogen car engine, and they have produced the hydrogen car. It's a very efficient car, and then emission is water. So this is also a very good thing. And next thing is that the Japanese engineers have produced the flying car. So the possibility that flying cars will come into the market is also high. So they expect that cars will come to the market somewhere in 2026 or so. And so you see, when you have flying car, of course you can drive it on the road, and also you can fly like a plane. So you see, and once the technology, like let's say if that happens, then such things will have greater demand. And then if you are those countries which produce motor cars using the 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 current vehicles on the road will become outdated. So that will be that and then along with those people who have stocked them, they are also going to be in trouble. What is one advantage of flying cars is that you don't need roads. You don't need roads. You can fly and then bring it home. But one thing is, landing. One of the problems in is landing. So there has to be, similar to airports, roads similar to airports. That will be a requirement, I think. So infrastructure also will change accordingly. So it's a kind of a revolution, a transportation revolution on the card. So you see, if new models comes, new design comes, new technology comes, stocking and keeping for a long time is not a wise decision. So, and then operation time equals setup time plus run time. Setup time is the time needed to prepare the machinery. So for to start production, runtime is the time actually spent on producing the particular item. And then throughput time equals average time for a unit to move through the system. Average time for a unit to move through the system. And then concept of velocity equals throughput time divided by value added time. So setup time and run time. Run time is calculated by multiplying the time required to produce each unit by batch size. Setup time is the time required to prepare the machine. So let's say you have considered serial boxing machine is producing at a rate of 30 boxes per minute. The runtime for each box is 2 seconds. Okay, here minute has 60 seconds. And then in 60 seconds, 30 boxes are produced. So then one box takes 2 seconds. Okay. To switch the machine from size 1 to size 2 is 30 minutes setup time. So then operation time to produce 10,000 boxes of size 2, you have 30 minutes times 60, then you have 1,800 seconds. plus, because this is the setup time, plus 2 times 10,000. So the total time is 21,800 seconds. So that is 363.33 minutes. So this is the operation time is 363.33. So the run time is now 2 times 10,000. That particular batch you produce 10,000 units. Assume 1 unit take 30 seconds to produce in a station. And then you see, so then you have, you see each station, 1, 2, 3, 4, 5, 6 station, take this diagram, throughput time equals 30 times 6. So 1 unit takes 30 seconds, and then you have 6 stages, and then 180 seconds, that is 3 minutes. Let's say if you put 2 unit buffer in front of stage 2, stage 3, stage 4, stage 5, and 6. Okay. Then what is the throughput time? So then all the units 1, 3, 4, 6, 7, 9, 10, 12, 13, 15, 16. So you have throughput time after including 2 unit buffer in front of second, third, fourth, fifth, and sixth stations. You have 16 times 30. So then it's 480 seconds. That is 8 minutes. 8 minutes. So in this one, this example, there are no buffer, so that any unit that enters this production, this production facility or production line will take the 30 times 6, that's 180, that is 3 minutes to come out. But with the buffers, of course, it takes now 8 minutes. 8 minutes. So then value added time is the time in which useful work is actually being done on the unit. And then in the second example with 10 buffer units and all operations are useful work. So velocity equals 8 minutes divided by 3 minutes. So value added time is 3 minutes, but then the throughput time is 8 minutes. So velocity you get 2.66. 2.66. Actually, velocity equals throughput time divided by value added time. So the best velocity is, when there are no delays or buffers, throughput time equals value added time. So velocity will be 1.
Excuse me.
Yes.
How can you take the 3 minutes as a value added time?
Here, in this example, each unit, let's say a new unit coming, okay? New order coming, okay? And then for the completion of that order, this should pass through stage 1, 2, 3, 4, 5, 6. And
Yes.
then each stage take 30 seconds. 30 seconds 6 times, then 6 times 6 is 180. 180 divided by 60, you get 3 minutes. Okay. So then in this diagram, you don't see any delays, so buffers, right?
Okay, sir.
Therefore, this is actually the value-added time is 3 minutes. And then with the buffer, there are buffers, 2 minutes buffer, 1, 2, 3, 4, 10 minutes, right? Buffer. And then the new unit coming will be out, when you order, let's say new order comes, and then it is completed after 8 minutes. Okay. This 8 minutes we calculated this way.
Yes.
You see, this buffer units also has to be processed, right? Buffer also has to be processed. Let's say this one at a particular time, a particular time unit is now here. Unit is in production, and then once this one is completed, it goes to this buffer area. And then next in line out of the 2 units will be taken into production. And then here also this one, once this is completed, the next in line will be taken, not the one that immediately come from this one. Okay, so that's how, the delay happens. So
Okay, sir.
new one coming will take, 16 times 30 seconds. So that's how you get 8 minutes. You got it?
Yes, sir. Yes.
Okay. And then we go calculate the velocity. So velocity for this case, with the buffer is equals 8 minutes divided by 3 minutes, that 2.66. Velocity don't have actually a dimension because it has to be calculated the same time dimension. Like if you are using minutes in the numerator, you have to use the minutes in the denominator as well. So the best velocity is 1. Let's say if we calculate velocity for this situation, throughput time is 3 minutes. Value-added time is also 3 minutes. So, and then if you 3 minutes divided by 3 minutes, you get 1. Okay. If inefficiency occurs, velocity becomes larger than 1. So here 2.66 is highly inefficient production line. Cycle time is average time between completion of units. So we discussed that earlier also. Throughput rate equals 1 divided by cycle time. Throughput rate equals 1 divided by cycle time. Efficiency equals actual output divided by standard output. Let's say assume the cycle time is 30 seconds, then throughput rate is, the time available. Let's say in a minute, in 1 hour, let's say in 1 hour, you have 60 minutes and 60 seconds. So divided by 30. So then you have throughput rate is 120 units per hour. So this one also it's 120 units per hour. And then let's say 2 units per minute. If it is minutes, it's 2 units per minute. So this one is beside. So if it is minutes, then 260 divided by 30, that means 2 units per minute. So that's how we calculate throughput rate. So here Throughput rate is 1 divided by cycle time. Here, if you take this one in terms of hours, or, you have to decide this one. This one, is it in hours or is it in minutes? Is it in days, peaks, and so on? Efficiency is actual output divided by standard output. Okay, throughput rate. You understand throughput rate? Suppose the standard is 30 boxes per minute and actually 36 boxes are produced in the minute. Then the efficiency equals 36 divided by 30 multiplied by 100, that is 120%. Process performance matrix. So productivity equals output divided by input. The term utilization, time activated divided by time available. Time activated divided by time available. Let's take cycle time. Suppose you had to produce 600 units in 80 hours to meet the demand requirements of a product. What is the cycle time to meet this demand requirement? So then there are 4,800 minutes in the 60 hours, right? So then 4,800 minutes in the 80 hours. So the 80 multiplied by 60, you get 4,800. So the average time between completion of completion would have to be cycle time 4,800, that is time available, divided by number of units, that's 600. So the cycle time is 8 minutes per unit, 8 minutes per unit. And then process throughput time reduction. So what we can do is we can perform activities in parallel so that we can reduce the throughput time. And so by changing the sequence of activities also, it is possible for us to reduce the throughput time. And then by reducing interruptions, also it is possible to reduce the throughput time. So this ends the the theory part of this one. So if you have questions, you can ask. Any questions? So then I am going to, if you don't have questions, I'm going to share a question, exam question. So this one, you can, you read this question, and try to work out the answer. Can you see the question?
Yes, sir, you can see that.
Okay, you read this question and try to answer it. And I will give you a break. Okay, I will give you a break Because I did not have my lunch, so we'll have a break, and after the break, I will discuss the answer for this one. In the meantime, you can try to answer. So this there was a question posed in the chat. Great. Throughput rate is, 1 divided by cycle time. Here, you have to take one, let's say first, you need to observe this, uh, so here, the production cycle time is 30 seconds, okay? 30 seconds per unit. And then 60, this 60, this is 1 hour, right? Here we are going to calculate the rate, right? Then rate is calculated number of units per hour, okay? So then this is, in this one, throughput rate is, here you have a number, right? This 1, okay? This 1 can be 1 hour, or can be 1 minute, 1 day, 1 week, 1 month, like 1 year, okay? Like that, okay? So then, depending on this one, the dimension that is used in the one, you have to calculate, for example, here 1 is an hour, okay? When let's say you want to calculate the throughput rate using hour, so then 1 hour has 60 minutes, okay? This is why you get 60, and then you have to translate that into seconds, because cycle time has been calculated in terms of seconds. And then 1 hour has 60 multiplied by 60 seconds, 60 minutes, and then minutes has to be converted into seconds. So then 60 times 60 divided by 30. So then throughput rate is 120 units per hour. Okay. So this question, you tried this exam question, only part of exam question. So you read the question, and then you write down your answers, and I give you a break, and after the break I will discuss the answer. Okay. Can you see the question?
Yes, I can see.
Okay, did you read the question? Are you there? Did you read the question?
Yes, sir.
Okay, but now let's see. What is the current output of the process? You can see here 60 customers, 100 customers per hour orders are taken. And then when it comes to here, 80 customer orders are processed. So then there will be 20 customers waiting every hour here in this, let's say, waiting line. And then picked orders per process 60 customers per hour, and then there will be 20 customers per hour waiting in front of the packed orders. And then the output will be 60 customers per hour. So then current output will be 60 customers hour. And then how long will the picking and packing operation have to work if we have the day with the maximum orders? So then the processing is so then from 7 a.m. to 7 p.m. there are 12 hours. Then 100 customers per hour orders taken. So then total orders, total number of orders per day equals 1,200. And now picking operation. Picking has to work so this means 15 hours a day. Packing has to work 1,200 divided by 16. That is 20 hours a day. what is the maximum number of orders waiting to be picked? Answers to this one. That is, in front of the see 1200, we got 100 times 12. So this equals 100 per hour multiplied by 12 hours. 7 a.m. to 7 a.m. to you can see. You see, Salim Widget Warehouse takes orders from 7 a.m. to 7 p.m. 7 a.m. to 7 p.m. you have 12 hours. So then 20 orders per hour. Waiting 20 orders per hour. At the end of 12 hours, there will be that is 100 minus 80 times 12. That means 240 orders left. And that is the maximum number of orders waiting to be packed. Again, that too is 20 per hour. 20 orders per hour. $20 per hour. And then at the end of the day, there will be 600 orders completed. Balance 600 are waiting. 720 orders. At 7 p.m. there will be 240 orders in front of packing operation. At 7 p.m. there will be, you see, packing and picking, the difference, the work rate difference is 20 customers per hour. So for 12 hours, there will be 240 customers. And actually, there is another 240 in front of a picking operation. So the totally they have to pack total including 240 orders in front of picking, there is waiting waiting to be back. And then if we double the capacity, what impact does this have on answer in part 2 and 3 and 4? If we double the packing capacity,
Yes, question, sir.
yeah,
So in six, in six part, in the five questions number 5, we get picking hours as 15 and the packing hours as 20. But in the why we take in here 12?
I think your rate is 60 customers per hour. No?
Yes, sir. I am asking next question. The to calculate waiting order, why we take 12 hours? Can't we get 15 hours and 20 hours?
In 2.
Yes, sir. I'm asking question number 3 and 3.
3.
3
What
and
is the
5. 3 and 4.
Yeah,
Yes.
4. What is the maximum number of orders waiting to be picked, right?
Yes.
Then you see 20 orders per hour waiting.
Yes. We it's not relevant to second part. I thought like that.
To accept 1,200 orders in the day, right?
Yes.
And then at the rate of 80 customers per hour, 80 orders per hour, you have to work 15 hours a day.
Yes, sir.
Okay, but the working day is actually from 7 a.m. to 7 p.m. That's 12 hours.
All right, sir.
That's why 100 orders. You are accepting 100 orders. You can see. We should see the diagram, right? See, 100 customers per hour take orders. So then for 12 hours, you take 1,200 orders. And then peak orders work 80 customers per hour. That is slower than this. So then here 20 customers have to wait.
Yes, sir.
Every hour there is 20 customers waiting. So after 1 hour, you have 20 customers, right? After 2
Yes.
hours, you have 40 customers.
Yes, sir. Yes, sir. I got it.
After 3 hours, 60 customers. Altogether, at the end of the day, you have 240 customers. 240 orders waiting at the end of the day. So you got it?
Yes, I got it.
And then the packing also same. Packing, there will be 240 orders in front of packing operation, including 240 orders in front of picking. There is 480 orders waiting to be packed. Okay,
Right,
because
sir.
packing works at 60 customers per hour rate. No? So then for 1,200 orders to process at the 60 customers per hour, you need 20 hours a day. Now, if we double the capacity, this one will be 2 will be how long picking? Okay, picking has to work anyway 15 hours because it's not changed. Packing has to work also because picking packing is now faster. Packing works 120 customers per hour speed, right? This is the packing capacity when you double. So then the processing is 120 customers per hour. But then, the orders, final order is completed after 15 hours. All the orders are picked after 15 hours. Therefore, this is 15 hours you have to work. Packing operation, packing staff will have to work 15 hours. Actually 10 hours, but then, their value added time is 10 hours. Yeah. Ten hours with 5 hours waiting. Waiting, I see throughput time is 15 hours.
So how, excuse me, sir. Excuse me, sir.
I am understanding. Okay.
Uh, how you took that 10 hours as valuable time?
Now orders, you see, you have 1,200 orders. Packing capacity is double. That means they can process 120 customers per hour, right? But you have 1,200 orders. 1,200 divided by 10. So this equals. So this one you got. This equals. So we got 1,200 divided by 10. Sorry, 12. 120. So that's how we got 10 hours. Their work speed is 120 customers per hour. Number of orders is 1,200. So value added time is 10 hours. 5 hours waiting. With 5 hours waiting, throughput time is 15 hours. And someone is asking, so 15 hours, you have to work because, the picking rate is 15 hours a day. Okay. The order taking rate is, 100 customers per hour. Then at the end of the day, Salim would have taken 1,200 orders. So at the rate of 80 per hour, the picking has to work 15 hours. And then packing, the work rate is 120 customers per hour. But therefore, the packing will actually work, value added time is 10 hours. But then, the work has to come. Work has to come to packing. From picking takes 15 hours, and then work has to come for packing. So that's how the answer is for.
So excuse me, sir. Sir, here how you took with 5 hours waiting throughput time is 15.
Here, the 5 hours here, 15 hours is the picking time. And then packing operation is operating very fast now. At the rate of 120 customers per hour. It's even faster than order taking. Okay. So therefore, when the picking orders come, they complete quickly. And then, but then picking comes late. Picking is the bottleneck operation now. And then all the orders of all picking orders are completed after 15 hours. And then the packing operation is working fast. But then the actual work required by packing is 10 hours to operate 1,200 hours. And then the balance 5 hours packing will be idling. So waiting in the sense idling. With 5 hours, waiting. Okay, with 5 hours waiting, throughput time is 15 hours. Got it? And then what is the maximum number of orders to be picked? So that will be 20 orders per hour. At the end of 12 hours, there will be 240 orders waiting. That's correct. It's same. But packing, packing now, you see, waiting will be 0 orders per hour. Because the packing is working fast, because now the capacity is double. There will be 0 orders. 0 orders in front of packing operation. So there won't be any order waiting in front of packing operation. So there will be 0 orders in front of packing operation because packing is working fast. Therefore, there are no orders. All orders that comes, will be taken to process. So that's how it is. Someone is asking It's 480. How we got the 480? You see, 20 orders per hour, and then there will be 240 orders in front of packing operation, because the 20 packing is slower than picking, and then picking operation is working 80 customers per hour. Packing is working 60 customers per hour, and therefore, at the end of the day, there will be 240 orders per hour waiting, waiting in front of the packing operation. But including, including the 240 orders waiting in front of the picking operation, that picking has not come, but at the end of the day, anyway, they have to complete 480 orders. So this is what, this is how this 480, 240 and this 240 put together become 480 orders waiting to be packed. But remember, these 240 orders are in front of picking, not in front of packing. But anyway, they have to complete those 240 also. So then, finally they have to complete the 480 orders anyway. So that is the answer. That is how we got 480. Okay, did you, is it okay now? This is actually a simple question. If you understand what it won't take, much time. And then I'm going to move to learning curve. Okay, learning curve concept. Predict reduction in manufacturing cost or direct labor hours as cumulative production increases based on empirical evidence rather than theories. So the principle of learning is actually came from empirical evidence. It's not theory. So if you take, let's say 85% slope, so this one, so here, horizontal axis, you have cumulative units produced. The vertical axis is number of dollars, and then so I'm going, let's say this one. So let's say 80% learning. The learning curve principle is like this. Learning curve principle. Every time the output is doubled, the learning, the processing time will be improved by the learning rate. So this is the principle. Now let's say if first unit takes, let's say 80% learning, let's say at 80% learning, at 80% learning, first unit will take, let's say 100 hours. Second unit takes 80 hours. Fourth one takes 80% of 80, that is 64 hours. Eighth one takes 64 times 0.8. So that equals actually 51.2 hours. So this one we got. So this one we got 64, we got that by 80 multiplied by 0.8. So that's how we got this equals this, we got 100 multiplied by 0.8. So you see, every time the output is double, the processing time will be improved by the learning rate. So this is the learning curve principle. And now this one, at 80% learning, first unit takes 1000 hours. Second one takes 800 hours. Fourth one takes 640. Eighth one takes 512. 16th one 410. 32nd one 328. And then if we draw it as a diagram, you see we get this shape. Learning curve is a, you see, it's a negative exponential curve. Okay, so the time taken will be improved. You see, if the slope is very high, that is learning rate is fast learning rate. The slope is so if you get a more flat curve, that means the learning is not improving, because maybe when the employees are at, for example, a
Recording in progress.
times x to the power n. So x equals the unit number. Okay, first unit, second unit, third unit, like that. Let's say if it is first unit, then x equals 1. Second unit, x equals 2. Third unit, x equals 3. Fourth unit x equals 4. And then yx is man hours to produce the xth unit. How long it takes to produce the xth unit. K equals hours to produce the first unit. N equals log b divided by log 2. Here b is actually the learning rate. So we write b as a fraction. Okay, that is log 0.8. If b is 80%, then b equals 0.8. Okay, so you see we write it down as a fraction. So then logarithmic equation, if you take log for this one, then log yx equals log k. Log k, actually this has to be plus log k plus n log x. Log k plus n log x. But since n is going to become a negative one, this should be a negative one. So then the cumulative units produced, the shape will be like that. A cumulative log is in log term, you get a straight line. Let's say example, k, let's say k equals yx equals kxn, n equals log b divided by log 2. For 80% learning curve, b equals 0.80. Now log 0.8 divided by log 2 equals minus 0.3219. Let's say you have 0.8 and take log. .8 log equals minus 0.09 something divided by so this division comes as minus 3219. So this is this log is not natural logarithm. It is when you say log, it is base 10, right? So you take the base 10. So then, for example, y1, if you substitute in the equation, y1 first unit takes, 1 to the power any number is 1, therefore it's 1000. And then second unit takes y2, 1000 times 2 to the power minus 0.3219, that is 0.8. So this equals 800. Third unit, you can calculate for odd numbers, like the middle numbers also using the formula. So formula is a very useful method of calculating the time taken for units. And now, let's say b equals 90%, then learning curve is more flat. 80% is in between, 70% is even more steep. See? Forces behind the learning curve: increased labor efficiency, And then process innovation and methods improvements. So you have substitution effects, product redesign, standardization, economies of scale, shared experience. And then estimating learning curve parameters, the concept applies to an aggregate rather than to individual operations. First unit hours rarely known in time to develop the curve must estimate far in advance. So normally on an ongoing process, we don't know how long it takes for the first unit, right? But if you are starting a new one, and then you can find how long it takes for the first unit. The slope can be estimated by least squares regression. That is a possibility. Okay, the comparison should always be made to similar product processes in industry data usually available. Extensive pre-production planning should result in lower, flatter curve. So actually, once employees are better trained, and then there will not be much improvement in the learning. It's not, therefore, you get a flat learning curve. Flat learning curve means actually you are doing, your employees are better trained. Flat learning curve means steep learning curve means there is a lot to learn, so therefore they improve faster. So that's what it means. So estimating learning curve parameter, let's say, so if you have a steep learning curve, this is a log 1, right? And then if the slope is high, that means little planning. You just started and then employees are learning naturally. But then if you have extensive planning, and then there won't be much to learn, therefore the learning improvement will be not so high. So therefore you get a flat learning curve. So this one is, for example, about a 90% learning, and this one is about a 85% learning, or maybe 80% learning. And then manufacturing strategy and the learning curve, capacity expands automatically. See, when the learning, when the workers perform faster, our production capacity expands automatically. Break-even points reduced automatically. Worker compensation plans should account for learning effects. So that is this is something that for when you achieve better performance. Let's say if the employees produce, let's say if the first unit took 100 hours, and then it comes to, let's say, 80% learning, fourth unit takes 64 hours. So then the production is faster. So then when the number of units produced are more, automatically company income goes up. So then, this additional income that is earned has to be actually shared with the employees. Certain percentage of it should be shared with employees. The companies should have good compensation plans, so that everyone is benefited for better performance, so that the pay satisfaction, and also pay satisfaction is there, and also recognition. Satisfaction due to recognition is also there. So it's better to pay the employees. Always, paying employees a better salary better salary is I think it is a kind of a good virtue. It's a good thing. But many employers don't look at it that way. Some people, actually, these organizations who do not pay their employees well, they are not going to perform well either. Because, low pay is related to extreme level of dissatisfaction and suffering. And people will have to undergo a lot of hardship to live also. So I think better pay means, employees are happy and the company culture will be happy. So in the society also, they have good recognition, I think. So the sharing performance, additional performance benefit is, I think, is a must for organizations' future. Although we discuss these things in classes, I have never seen our students applying these concepts in the industry. So if I recall some of my two older graduates, there is a I'm talking this thing keeping in mind, two graduates who are leading businessmen in the country. The problem when I speak to their employees, I find that these two guys don't pay well to their employees. So they use various tactics, including political relationships to do business well. But their companies, they don't do well at all. Because I think it's kind of unfortunate for our faculty. Our graduates don't apply, this what we are discussing in the classes. So therefore, they don't do well. Their organization future is also, I think, bleak because what I see is that these guys make deals with the politicians and then try to looking at short-term profit. But they are not looking at long-term sustainability and long-term survival is at stake, I think. At some point, the learning curve will plateau anyway, like I showed you. For example, like, see, if you go back to a curve. So let's say, see, this is this curve. This is 80% learning curve. And after 30 second unit, curve is becoming flat. Let's say you started measuring time at the 30-second unit, and then the new learning curve is, the remaining part. So that is actually a flat one. See, anyway, at some point in time, learning curve become flat. Learning curve applications, we can have it, production planning, economic order quantity planning, price forecasting, and then competitive bidding, income reporting in accounting, planning, warranty maintenance, and then forecasting industrial accidents, forecasting automobile accidents on new roads. Okay, so this way. And I'm feel discuss an example. Let's say exam question. Can you see this question?
So upper part we can't see.
A question starting from an initial pilot run of 10 units.
Yes, so we can see that.
Okay, that is the part you have to read. So we'll discuss this. Read the question. Maybe if you, for calculation purpose, I think it's better you take it down. Better take it down and, prepare a note. To take down the question, Did you take down the question?
Yes, sir.
Okay, I will work out the answer in the Excel sheet so that the I will work out the answer here itself. Okay, so now you see the principle of learning is every time you double the output, the learning will be improved by the learning rate. Okay, so then let's say from 1 to 2, 1 to 2, the improvement. You see learning rate. So I will instead of I will have a table. Let's say from 1 to 2. 1 to 2 learning rate will be 29 29 divided by 39. So this equals 29 divided by 39 equals 29 divided by 39 equals 0.743. So this equals 0.743. And then 2 to 4. 2 to 4. Two, it's take 29. 4, it takes 19. So the 19 divided by 29, then 19 divided by 29, you get 0.655. And then 3 to 6. 3 to 6. Three takes 23. 6 takes 16. This division is 16 divided by 23. It's 0.6956. That is 696. 696. And then 4 to 8. 4 takes 19. 8 takes 13. The division actually 13 divided by 90. It's 684. So we have then 5 to 10. 5 to 10. Five takes 17. 10 takes 12. Division takes 12 divided by 17. You get 7.706. 706. So now, we take the average. So we have we have 1, 2, 3, 4, 5. 5 observations. And then we have to add this one. Plus. So this equals 0.743 point 743 plus 655 0.699 96 plus 0.684 divide this by 5 you get 0.696 0.6969 something 696 77 like that. So this is approximately equal to 0.70. So the answer is learning rate is equals 0. That is actually 70%. So learning rate is 70%. So this is we have answered the first section. Section is according to Python, what is the estimate of the learning rate? So if you have questions, you can ask. I'm going to for the next section.
So excuse me,
Yes,
why sir we didn't consider 2 to 3?
2 to 3. You see, the learning curve is curve is defined as every time you double the output, the time will be improved by the learning rate. So therefore,
Okay.
2 to 3, you don't get a doubling situation. You
Okay.
get
That's why sir you consider as 2, 4, 6, 8, 10
yes.
based on the
1 to
principle.
1 to 2, 2 to 4, 3 to 6, 4 to 8, 5 to 10. These are all the numbers that where you have the doubling, output doubling situation. Okay.
Okay, thank you, sir.
And then, next question is how much time will it take to produce the first 50 units? First 50 units and next 90 units. Okay. So then I'm going to use the table. We have a table, right? For this, we need to use the cumulative table. So, can you see the table? Cumulative table?
Yes, sir, we can see that.
Okay, so now, we have to calculate first 50 units, how long it takes for the first 50 units. Here in this table, first unit takes 1. Okay, first unit take 1. That's why you have 1 here. So under the 70% column, so we need to come down till the 50th unit. So we get the number as 12.8281. So then 12.8281.
Sir, where we can obtain this table, sir?
Yesterday I sent to the MB office. You could have got it. Ask them to upload it if they have not uploaded.
It has uploaded.
Then, first 50 unit takes 12.8281. So multiply this by the, here in this example, first unit takes 39 minutes. So then time for first 50 units equals so this one, you can use the calculator. $12.8281 multiplied by 39. We get 500 point. 500 minutes. Okay.
Sir, why we multiplied it by using 39?
39 is, it got in the question. 39 is the time for the first unit. In the table, it is assumed that the time for first unit is 1. So you have to multiply this by
Yes, sir.
for the first unit. So then you get, is the time for first 50 units, all of them, right, together. And then next question is time for next 90 units. So here, in this question, we have got time until the 10th, first 10 units we have got the time. So then, we need to subtract. So this, we have time for first 100 units minus time for first 10 minutes. So then you get, time for the next 90 units. So then, we can see the table. table. I will share the table, right? Okay, so now first 10 minutes, there are two ways of finding the along the 70% column, you come down. Oh, good. Click this one. It is let me multiply this by 479.96. That's 470. And then we need to find time for next. Let's say we find time for first 10 minutes. Time for first 10 minutes is here. It is actually 4.93. You can take it down somewhere. Time for first 10 minutes is and then we find the time for first 100 units. That is 17.7907. So we say we have to multiply this by time for first unit. So then you subtract time for first 100 units is 17.7907 multiplied by 39. Time for first 10 units is 39 multiplied by 4.9318. So this actually the 39 multiplied by 4.9318. You can instead of this you can substitute by adding 39, 29, 23, 19, 17, 16, 15, 13, 13, 12. This number, by adding the numbers also you can replace, okay? Either way. So then I'm going to use the calculator.
So can't we take that figure directly from the cumulative table, 90?
No, you can't because first 90. So here, question is next 90 units. Next 90, not the first 90 units. First
Okay, sir.
90 you can take next one, but no, it's not possible. So then I'm going to 17 point calculate is 17.7907. Zero 7 minus 4.9318. You have 12.8589. 89. So multiply this by 39. Multiply this.
Mega.
12.8589 multiplied by 39. You get 501.49. Approximately 501 minutes. Okay, so this is the answer. And then, we have a question, what will be the average time to produce first 1,000 units? See, you go through the table, right? So, So now I am no. Question here is not about the 50 from 50 to 50 to 100. Then if it is the case, we have to start from first 140 minutes and then first 50 minutes. That way we can calculate that answer. But the question is about first 10 minutes we have given and the next 90 minutes we have to find. Okay, so we somebody is asking, how we got 17 point something. You see, can you see the table?
Yes, sir.
Okay, so then first 100, right? So you find the first 100. You see, first 100 units take 17.7907. So that's how we got that. And next, the question is, you see, if you go down the table, right? So go to the bottom. So when you go to the bottom of the table, calculating time for next 9 days. No, that's not possible. So this table actually so this table has only the last number is 1000. 1000. So question is 1000. You know, first 1000. First 1000. First 1000 it takes 57.4006. I'm not sure what the question is. What will be the average time to produce the first 1000 units? Okay, for the total time for the first 1000 units, so when I read it on the table, first 57.4006. So equals 39 multiplied by 57.4006. So this equals 50.4006 multiplied by 39. You get 2238. 38 minutes. So then we have to answer average time to produce first 1000 units. Because we divide this by this number by 1000. Divide by 1000. You get 2.238. 2.24 minutes. So this is the answer. And like, I have given a question in this answer to this question like it's like this. Let's say how much time will it take to produce 2000th unit? Let's say you have a question. How much time to produce the, let's say, 2000 unit. So then, you have to use the formula that is you see, we always multiply by 39 because first time for the first unit is 39. So then here we use the formula. There is a problem with the signals. So use the formula let's say this equals 39. 39 shall we 39 x to the power 2000. So 2000 to the power log 0.7 log. So So then y 2000 equals 39 times 2000 to the power log 0.7 divided by log 2. So when you point 7 log so let's say 2000 to the power to the power 0.7 log divided. It's 1.023. So you have to double check it. Mm. $39 multiplied by 2000 to the power 0.7 divided by 2. Point 781. So minutes. So this is how, here in this situation we have to use the formula. Okay. So if the numbers are not available in the table, you have to use the formula. There is lightning happening. So therefore, I'm going to stop the lecture. So if you have any questions, you can ask next week. Okay.
Okay, sir. Thank you, sir.
So you can ask questions next week.
Thank you, sir.
Recording stopped.
Thank you, sir.
Thank you, sir.
Thank you, sir.